Thanks for the introduction. And I heard everyone had a coffee and we can like wake up for the last part of the talks today. And as Freya said, I'll be talking about something a bit different. I'll be going into the deeper paths, and I'll also be looking at some ultramafic rocks. So I know, shocking, no garnet. But so yeah, I'm kind of looking at what this might say for the early part of Earth's history and water cycling in the Archean. Yeah, so this is a figure from Richard. Unlike Jacob, I knew Richard would be here, so I thought I better put one of his figures in. Otherwise, I get kicked out of the conference or something. But here's just an image of deep time going from the Hadean, the Archean, all the way through to present day. And these are all just suggestions for when plate tectonics began on Earth in black. And why do we care about when plate tectonics began? Well, basically, that's probably how we made the continental crust, via some form of plate tectonics and plate interactions. So if we look at the modern day, we all know this figure very well. This is just a volcanic arc where we have subduction of usually oceanic crust, and a bunch of processes in here which are basically driven by dehydration in the subducting slab. So in this figure, I've put antigerite and chlorite out in the ultramafic rocks as a primary way to get fluids out of the subducted material and into the mantle wedge, where we can then undergo a series of partial melting, fractional crystallization, underplating, whatever you like. But we make our continental crust, which is on average diuretic to andesitic in composition. But in the Archean, if we now look back in this sort of pink area here, like there's a lot of suggestions that plate tectonics must have begun in this time. But there's a lot of still outstanding questions. Did we make our crust in the Archean the same as we make it on the modern day in arcs or not? And I'm not even going to pretend to try and answer that at all today, but I will bring up some main questions, which is what was the continental crust made of in the Archean? How was that continental crust made? And what was the role of water in the solid Earth, and how was it transported? Because we know that today water is incredibly critical for making new crust, but was this so in the Archean? So for those of you who don't know what an Archean craton looks like, they usually look something like this. This is just a nice figure where we have these big sort of more felsic dome materials, which are made of TTGs. Tonalite-Trondhjemite-Granite diorites, and they're usually sort of wrapped by these greenstone belts, which are made of lower grade materials that are usually green schist to amphibolic facies. So with that general structure of an Archean craton, we kind of say that the continental crust was mostly made of these TTG rocks. And that's because they make up a lot of the surviving Archean crust, around 80 billion%, and also they're very silica rich, they're very buoyant. So we like to say that's probably what a continent was. So how are they made? This is a bit of a very broad question, but over the past few decades, people are starting to really think that these TTGs were made from water-present melting of basalts, and at quite low temperatures, mostly around 750 to 950 degrees Celsius. So these TTGs, they're very sodium-rich rocks, as we can see here, and they were definitely formed by some partial melting, fractional crystallization of basalts. The key kind of point is, though, is that the basalts themselves cannot provide the free water. So as I kind of mentioned, differences in source chemistry, melting depth and temperature, fractional crystallization, there's a lot of things that cause all the differences in TTG compositions. So it's a bit of a broad statement to say they come just from basalts, but there's a lot of evidence that that's the case. So thinking about plate tectonics in the Archean, this is just a sketch I put together. Please do not take this with like a kilogram of salt, because no one knows what was happening back then, but these are just some of the sort of ideas for how we could do it. Maybe we did it in these sort of very modern subduction things or underfrosting of materials. Perhaps we built these TTGs in oceanic plateaus. Maybe there's some interactions with plumes, delamination, all sorts. But the key question for me really is, what is the source of free water for wet basalt melting and TTG generation? So now I take us to the serpentinized ultramafic rocks from the Archean. So in the Archean, we don't have nice ophiolites, perhaps like we do on the modern Earth, but what we do have is these komatiites, which are found in greenstone belts. So they're erupted ultramafic rocks. They have very high magnesium contents. And many were erupted underwater. So therefore, a lot of them are immediately hydrated by serpentinization reactions. And this is an image of some basaltic komatiites showing really nice pillows from the Pilbara Craton in Australia. When they erupted, they would have contained very coarse, abundant olivine in these beautiful spinifex textures, a lot of glass, probably pyroxene spinels, these sort of thing. So for those who don't really know what a greenstone belt looks like, I didn't before I started this project. This is just an example from South Africa, which has some really lovely exposures of greenstone belts to sort of show you that they're interlayered. So these darker materials are very komatiite-rich layers, so very much dominated by these ultramafic rocks. And they're usually interlayered with things like basalt, cherts, felsic tuffs, those kind of things, and even banded iron formations. So they seem to have been formed in a submarine to subaerial environment and record these interlayered basalts and ultramafic rocks. Where do we find them? Well, in Archean cratons, of course. So this is just a map of Archean cratons from around the world, and each of these little points represents a komatiite or a basaltic komatiite that has a whole rock geochemical analysis attached to it. So this is actually a large database of geochemical analyses that I'll show you in a bit. As I said, now these things are green schist amphibolite facies, so they don't look like beautiful fresh lavas anymore. They usually look like this. So you can see these like pale sections. They're the old olivine crystals, which have been replaced by usually serpentine, usually antigerite and chlorite. And there's also quite abundant tremolite or amphiboles in the matrix, along with other things like magnetite, ilmenite, titanite, these kinds of minerals. But of course, the first thing you'll notice here is that they are extremely hydrated, with antigerite and chlorite containing up to 12% water and amphibole around 2. So they're incredibly hydrated rocks. And if we just look at a few representative samples from around the globe, we can see the H2O budget, which is mostly contained in the chlorite and antigerite, ranges between 3.5 weight% to almost 9 weight% water. So very spongy rocks. If we then go back to that big geochemical database I showed you, so this is around 5,600 geochemical analyses, and we plot them, a mean of them against LOI. So using LOI as a proxy for hydration or water content. And we plot them against XMG. Here we can immediately see that the basaltic komatiites, which fall down here, so with an XMG of less than 0.75, tend to only have 2 or 3 weight% water. And I think we'd expect the normal tholeiitic basalts to look around the same. But the komatiites, especially as you increase the XMG, can go way up to 9 or so weight% water. So it's nice that the entire geochemical database kind of agrees with the representative samples that I and other people have been studying. So of course, I have to show a phase diagram. So we've seen all the rocks now. They're green schist facies, amphibolite facies, but what happens if we continue to bury them and metamorphose them? What are the key dehydration reactions and how much water do they release? So this is a phase equilibrium model of a nice representative komatiite from the Barberton terrain in South Africa. And essentially what I want you to notice are these colored lines, which are the release in weight% of water. So we go all the way down from 1 to 6 weight% water released up here. And the kind of neat thing is that these reactions are very, very vertical in PT space. So they're very much temperature dependent. So if we look along a key sort of thermal gradient from the Archean, or just a transect through here, which is represented by this purple line, you can sort of see the key reactions. So down here at temperatures of 500 degrees, we have antigerite or serpentine breakdown. As we continue to prograde metamorphose these rocks, at temperatures over 700 degrees, we have terminal chlorite and tremolite breakdown. And this basically, because this axis here is the fluid release in weight%, this basically can release up to 5 weight% free water at quite high temperature conditions. So just to put all that information kind of together, this is the same phase diagram as before with the release of water in weight% from this study. These are the PT points from Mike Brown and Tim Johnson's database from the Archean. So I just kind of wanted to say, okay, in the Archean, what were sort of the crustal conditions of metamorphism? They fall somewhere in this realm. So just to constrain that into this section of the diagram. And then, of course, if we thinking back to our basalts, we put the wet basalt solidus. This is the experimental wet basalt solidus here. And you can see immediately that the main conditions of komatiite dehydration are quite far above the wet basalt solidus. And this is sort of a range of temperatures of TTG formation, somewhere between 750 and 950 degrees Celsius. So basically what I would think this is saying is that if we have our interlayered basalts and komatiites in our greenstone belt and we're prograde metamorphosing them, the komatiites can produce a lot of free water, which can then infiltrate the basalts and create quite voluminous wet basalt morphing. So thinking back to our current day, so, you know, in the current sort of Earth situation, the dehydration of serpentinites is one of the key ways we can put water into the mantle wedge and create our continental crust. Perhaps in the Archean, it was also the same, serpentinized komatiites, however, mostly in this time tremolite and chlorite out rather than antiquarite out, may have been the source of free water to melt wet basalts and form TTGs in the Archean. So thank you.
Yeah, I bet the komatiites sort of sourced from their wraps. Can you not see the same thing with the basalts?
You can, absolutely. So I think there's a nice combination of the wet melting with free water, but also amphibole with dehydration melting in the basalt. So by the time the basalts are at these conditions of 750 degrees or so, they're like high temperature amphibolites. So maybe they're like amphibole garnet. The only way they can really melt is by amphibole dehydration. And that doesn't create large volumes of basalt. Of melt from the basalt, sorry.
It's made the green chest, that's the dehydrated.
Well, you might see the wet solids from a tiny bit of fluid, intragranular fluid, but you still won't create huge volumes of partial melt from that. I think it depends which experiments you like, but they seem to call for at least 1 weight % free water. So I don't think at those conditions you'll have that within the basalt itself.
Would you expect brucite to be stable for any of these properties?
It's a good question. Yeah, no, that's a really good question. Unfortunately, all of the rocks, the komatiites, are mostly above, I think a lot of them are above brucite stability. Interestingly, we don't see metamorphic olivine though, which would be what you would get if you, yeah. So I think a possibility is that maybe, yeah, they're not quite the right compositions to make a lot of brucite, but something to look at. Yes.
The serpentinites obviously have got the high magnetite content from the original serpentinization, and that means that they will have given off hydrogen and they've got a very reduced condition. So do you see anything about melting that is consistent with having rather different fluids reflecting that different redox environment to really make it serpentinite?
That is a really good question, because the hydrogen question is something I'm working on right now and is very, very interesting indeed. The thing is, we'd have to look in the TTGs to see the evidence of that, because we're kind of missing that middle part of the story, right? We don't necessarily see the basalts that often anyway, partially melting in the sequence with komatiites, etc. But on the oxidation state of the TTGs themselves, I have no idea if that's buffered by the basalts or if we'd see something from the extremely reduced komatiites. I'm not sure if you'd lose it along the way, but I think it's something worth looking for, definitely.
Yeah.
Have you looked at different ratios of komatiite to basalt? Because often these belts have a little bit of komatiite, a lot of basalt. And so even though you're producing quite a lot of water per cubic meter of komatiite, it may not be massive amount of water on the scale of the basalt. So if you looked at different ratios,
that's
how much you would knock up the melting in the basalt.
Exactly, that is a really good question. I've looked a little bit. It's not the easiest because greenstone belts aren't super continuous, but there's actually some new drill core from the Barberton terrain I'm hoping to look at in July to try to quantify that a little bit better. So definitely worth looking at. Does the kind of mass balance in a way, how much basalt would you melt and what volume would you melt? I think is a really excellent next question. Cool, great, thanks everyone.
Thank you very much.